Hello everyone, my name is Dr. Destenie Nock, and I am going to present to you today about an analysis of greenhouse gas emissions and air pollutants from the electric transmission and distribution systems. This work is a collaborative effort between myself, Destenie Nock at Carnegie Mellon University. I'm an assistant professor of civil and environmental engineering as well as engineering and public policy. I am collaborating with Dr. Kavita Sarana at the University of Maryland and Dr. Sarah Jordan at Johns Hopkins University. The motivation behind this work is the level of global CO2 and air pollutant emissions occurring across the world, specifically in the electricity sector. So in 2018, we saw 27% of emissions for CO2 emissions coming from electricity. So we have to ask ourselves, as we transition our energy systems, how will transmission and distribution efficiencies impact these emissions? In this graph, you see a log of the emissions from electricity generation, the CO2 emissions from electricity generation on the y-axis, and the transmission distribution losses as a percentage on the x-axis. The green dots represent countries that mention their transmission and distribution losses in their original NDCs, where NDCs are the nationally determined contributions. And the gray dots highlight countries that do not mention transmission and distribution losses in their original NDCs. So those green dots amount to only 32 countries mentioning grid efficiency in their greenhouse mitigation strategies. In contrast to this, 110 countries mention some form of renewable energy. So given that in the Paris Agreement, each country's NDCs, or nationally determined contributions, embody the efforts of each country to reduce national emissions and adapt to the impact of climate change, we see that there is a large gap in those that are focusing on transmission efficiencies. And these transmission efficiencies are important because if we are inefficient, then this can lead to overbuilding, meaning that we would need to invest more resources and costs into building out our renewable energy systems. Losses can happen for a variety of reasons. Transmission and distribution systems suffer from inefficiencies from technical losses, which could be just physical limits or losses from resistance, or even just aging. And they also suffer from non-technical losses, which includes pilferage, stealing, fraud, that sort of thing. So when I say compensatory generation, I'm referring to the number of power plants, the amount that power plants are required to generate more than 1 kilowatt hour to deliver 1 kilowatt hour to a consumer. And our guiding research question here is, what are the emissions outcomes of reducing T&D losses? So how much could we save just by upgrading the infrastructure we use to deliver electricity? One key distinguishing factor of our research and others that we've found in the literature is that previous work is looking at emissions per unit of electricity generated. So the system boundary includes the fuel supply chain, the delivery of fuel to the power plant, and electricity generated at the power plant. But we are focusing on emissions per unit of electricity delivered, and our system boundary extends previous work to look at the transmission and distribution, to include the transmission, distribution, delivery to the consumers. Within our system boundary, we have the mining, production, storage, and transport from different fossil fuels. We have the equipment, manufacturing, and transport of renewables. And our calculation also includes the construction of different power plants. Now, our main contribution is incorporating these transmission and distribution losses, which is that highlighted blue box that you see. And then that's going to impact how much kilowatt hours we need to to satisfy the consumer's electricity demand. We calculate T&D losses in the system using the following equations. So the percent of transmission and distribution losses, or NTD, is equal to the reported transmission and distribution losses divided by the total electricity generation for each region. And then the electricity generation associated with the T&D losses, or the compensatory generation, is going to be this UTD for power plant G. In previous work, Dr. Serrana and Jordan investigated the CO2 mitigation potential across in a global context. And they found that there was a large amount of emissions reduction potential in a lot of the large polluting countries such as China, India, and the US. Now, this work did not include the other air pollutants such as SOx, NOx, and PM, and so that's where this initial work is focusing. So we focus on SOx because, or SO2, sulfur dioxide, because that can lead to more frequent asthma attacks. We also include nitrogen dioxide, which can increase susceptibility of lung infections in people with asthma, and also airway inflammation. And lastly, we are including particulate matter, specifically PM 2.5, because these particles are small, they can get deep into the lungs and into the bloodstream, and there's sufficient evidence that exposure to PM 2.5 over long periods of time can cause adverse health effects. We focus on using life cycle emissions estimations from the literature, and we're using these to understand the life cycle air pollutant emissions impacts from the transmission and distribution losses and inefficiencies. The air pollution emissions associated with T&D losses, or E-loss, is going to be equal to the emissions factor that we're getting from the literature. So that's going to be the grams of air pollution, of air pollutants per unit of energy or kilowatt hours. This is going to be multiplied by the compensatory generation resulting from T&D losses, multiplied by the K, which is the scaling factor. We use the scaling factor to account for the efficiency of different power plants and how that compares to our efficiencies that we're seeing in the reported emission factors from the literature. The data is sourced from the IEA. We're using that for the world calculations, and then the EIA is used for US calculations. This heat map is showing you how the transmission grid efficiencies vary by country. And we see that in China and the US, it's considered to be pretty efficient with 6% or less transmission distribution losses. India is considered to be relatively inefficient at 18%. Within our work, the highest losses that we're seeing are 60%. That's going to be in Haiti. We see very high losses in South America and in Africa. These inefficiencies translate to overproduction. So for the three countries I mentioned before, we see very high amounts of compensatory generation just to account for the losses. In China, we see 381 terawatt hours for the year 2017. In the US, it's 244 terawatt hours, and in India, it was 261 terawatt hours. So this presents an opportunity to understand and a need to understand how these losses and this generation that we need to produce to account for these losses translates to air pollutant emissions. So a part of the air pollutant emissions it's affecting the air pollutant intensity. So this graph is showing you the sulfur oxide intensity. So that's going to be in grams per kilowatt hour on the y-axis, and the transmission and distribution losses as a percentage along the x-axis. To give you a sense about where the countries are, I've highlighted them here. Now, ideally, we would have countries moving towards the bottom right-hand corner, the bottom left-hand corner. So we want a low SOx intensity and a low level of transmission distribution losses. So bottom left-hand corner. Now we kind of acknowledge that this is an initial analysis, and we want to dive deeper in looking at how countries should focus their efficiency upgrades on what they're producing. And so, for example, with Haiti being in the upper right-hand corner, we see that it has a high amount of losses, but it also has a high SOx intensity, meaning that we would need to, or that the country should think about what types of generation sources they're using to supply their electricity demand. These box plots give you a sense about how the intensities of the different pollutants compare in a global context, we see that the 50 percentile range for emission intensity of SOx and NOx are very similar, but SOx has a much wider range of the emission intensities by country, and PM has a very tight range. Now, the PM might have a really tight range because of the coal plants. So as we know, many countries are phasing out their use of coal generation. So this would then lead to a much tighter range because fewer countries are using a large amount of coal generation. We acknowledge that while these can show us how the range varies when we look at countries and we assume the median emissions factor, but there will be a range of emissions intensities when we look at the specific countries and the min and max emissions factor ranges. To account for that, we use Monte Carlo analysis to estimate how air pollutant emissions estimations in the literature would lead to different outputs in our range of country air pollutant emissions. So this is just to remind you of our emissions calculation and what it represents. We assume that the literature estimates have triangular distributions, and then we run our Monte Carlo simulation for 10,000 trials, randomly sampling them to account for how these pollutants might range by power plant. This is giving you a sense of how our top 3 countries for the compensatory generation vary by pollutant. So we see that there is a normal distribution for the USA, but in China and India, for the greenhouse gas emissions, it's skewed to the right-hand side, and for the NOx emissions, it's skewed to the left-hand side. So this would actually indicate that we need to think about how decarbonization would be in line or not in line with the co-pollutants. This model is still in development, and our next steps will be to incorporate a functional unit to look at the intensities of these air pollutant emissions and how they range. I want to acknowledge that national policies will miss infrastructure at the subnational scale, and so an in-depth country analysis could be useful to understand how policies would change at the subnational region. To accomplish this, I'm looking at the USA, and losses in the US range from 2 to 5%. This translates to a range of 6 to 2,000 gigawatt hours for compensatory generation by state. So looking at the top 5 most populated states, we can see how the CO2 emissions, which are going to be the top row, compares to NOx emission ranges in the bottom row. I want to acknowledge that the CO2 emissions are kind of higher than NOx by a magnitude of 3, so just keep that in mind. But this is to give you how the range of uncertainty would vary by pollutant. So we see that in California, it has a very tight range, where Texas and Florida, for example, have a very wide range. And this is related to the type of energy generated within the border of that state. So the table shows you the percent of energy generated within the border of each state in 2019. And it also shows the percent of coal and the percent of natural gas. So for California, we see that it doesn't actually generate any electricity from coal, and a lot of it is coming from natural gas. But Texas and Florida have a large percentage of their electricity generation being produced by coal, and also a much larger percent of their energy generated coming from natural gas as well. So that coal usage is going to lead to a higher range in the NOx and CO2 emissions. We also see something similar for SOx and PM emissions. We see a very wide range for Texas and Florida in SOx and PM, but we see a tight range for California. And that's because California generates a lot of its electricity from hydropower. So we will keep investigating this. As I said before, this is an initial analysis, and we need to look at the emissions intensities on a per unit basis. So some conclusions from this quick presentation. This work has investigated the air pollution emissions associated with transmission and distribution systems at national and subnational scales. By addressing transmission distribution losses, we are not only looking at decarbonization, but also thinking about how co-pollutants can be reduced and how this can be accomplished through grid efficiencies. Incorporating T&D investments into electricity planning, when the countries do this, they can identify the most cost-effective and sustainable infrastructure solutions to decarbonizing their grids. Our future work will relate the impacts of these pollutants to a functional unit and investigate and compare how our results will be similar or different from the NETL Grid Mix Explorer. Thank you very much for listening. I hope that you guys have enjoyed this presentation, and I look forward to having any questions. Have a good day.